All right, so today we're going to talk about electron configuration. Okay, so electron configuration, you need to understand that every element on the periodic table has its own electron configuration. It's kind of like a code name. And each code name is made up of a number, which is the principal energy level, which we learned last unit stands for the period number, which is the same as the principal energy level. It's going to have a letter, which is going to stand for the sublevel, and there's 4 different sublevels you can have. The S block is group 1 and 2. The P block is group 13 through 18. The D block is group 3 through 12. And the F block is the rare earth metals down here. So the D block is the transition metals, the P block is over here, and the S block is group 1 and 2. And then the number of electrons is the superscript. So that's how you know how many electrons are in that sublevel. All right? And so if you're saying, well, what does this mean? You have to be able to look and see, okay, where's oxygen? Well, oxygen is in group 2, it's in period 2, and it's a P4. So oxygen's code would be 2P4, right? 2P4 would stand for oxygen. What would beryllium be? Beryllium would be right here. It'd be 2S2, all right? And then if you say, well, what is calcium? Calcium's right here. It's 4S, and it's the second one in S. Potassium would be 4S1. And then like bromine would be 4P5 right there. All right? And so you say, well, what do these stand for? Okay? These stand for the ending electron configuration, which means that's where the last electron goes for that element. Because we learned with Bohr, okay, there were certain energy levels that contained electrons. And Bohr was correct in that. He was correct that these electrons are in different energy levels, and only so many can go in each one. So you have 2, then 8, then 8, then 18, then 18, right? And those were where the electrons are. But he was wrong when he said they're in fixed orbitals. Electrons don't actually do that. They're not in fixed orbitals. They're actually in these sublevels, okay? And Heisenberg came up with this thing called the uncertainty principle that said that you can know the speed of the electron, which we found out from Einstein, which he did the speed of light. So you can know the speed of the particle, or you can know the location of the particle, but Heisenberg's uncertainty principle says you cannot know the speed and the location at the same time, because what you're seeing is snapshots. And so when you see these snapshots, you're going to see that the first 2 electrons in the atom are right next to the nucleus. So it's like pop, 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 pop. They're like popping around. And these are called its ground state. So these are the lowest energy levels right next to the nucleus. Then the next 2 electrons are pop, 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 popping around also. Okay, and that would be the next 2 electrons. Well, then the next 2 electrons are like popping further away from the nucleus, okay, like that. And you say, well, why are these shapes drawn like that? Those are the shapes of the sublevels that the electrons are most likely in. So the S block, okay, has the shape of a sphere. The nucleus is the dot in the middle, and then most likely those electrons are going to be really close to the nucleus, pop, pop, popping around. The P block, they're further away from the nucleus, okay? And so they're pop, pop, popping around here, all right? And there's actually 3 orientations of P's because there's 6 electrons. So there's a PX, there's a PY, and there's a PZ. So just like in geometry or graphing algebra, you have your x-axis, you have your y-axis, and you've got your z-axis. So there's 3 different orientations of P's. The nucleus is represented at the origin, and a PX would be like the region of space where the electron most likely is on the x-axis right there. If it was a PY, it would look like that. And if it was a PZ, then that region of space is going to be like that. All right? And so that's the P and the P orientations for the P sublevel. A D is a double P, so it's just going to be like a clover. All right? And then the F is a daisy looking thing, so it's going to have 8 lobes. And then there's an orientation of D's that looks like that. It looks like the peanut with a ring around it, and then this one looks like a peanut with 2 rings around it. All right? And so what you're going to see is each sublevel has a shape, and that is the shape of where the electrons most likely are. Okay? So that's when you say, well, they're in a shape. Like, that's just a region of space where those electrons are pop, pop, popping around. All right? So the sublevel has a shape, and then each sublevel contains orbitals, and the orbitals are where the electrons actually are. So the sphere, the S shape, has one orbital because there's a maximum of 2 electrons per orbital. That's the thing. Okay, so because there's only 2 electrons for the S block, okay, there's only one orbital. Right? The P block has 6 electrons total. So there's 3 orbitals. Because max 2 electrons per orbital. If you have 6 electrons, you can only have 3 orbitals. The D block has how many electrons? It goes up to D10, right? So that's going to have 10 electrons, so that means there's only 5 orbitals. And the F block, there's 14 possible electrons, which means 7 orbitals. All right? Yes.
So does the 2, 8, 18, 19, does that not correspond to your orbital?
It does, because the 2 represents the 1s2, right? There's 2 electrons. Then the 8 represents 2 s's and 6 p's. Then, which is on the outer shell, right? And then the 8 for the third energy level is 2 s's and 6 p's, which is 8. And then the fourth energy level starts 2 s's, 10 d's, and 6 p's, which is 18. Okay? So that's what that represents. All right, so backtrack, we've got our S block, our P block, and our D block. Now, for valence electrons, you're only going to count S's and P's. Because the D block, like we talked about before, remember I told you their valence electrons vary and that they have varying oxidation numbers, the charges, because of that. Well, the D block is actually 1 less than the S's and P's. So you're going to see that the order is going to be 4s, and following 4s is going to be 3d. Then it pops back out to 4p. Then it goes 5s, 4d, pops back out to 5p, 6s, and then it goes 4f, because the F block is energy level -2. So the D block is energy level, the outer energy level -1. So if it's 6s, then it goes 5d. The F block is -2, so it goes 6s, 4f, 5d, then pops back out to 6p. All right? And you're going to learn that in a second when we do electron configuration. All right, but so far you should know that every element has a code, and you should be able to tell me what that code is. So for iron, what is iron's code going to be? Iron's number 26. So you look on the periodic table, and it's in the D block, and it's 1, 2, 3, 4, 5, 6 in the D block. So it's going to be what? 3d6. You say, wait a minute, it's in the 4th energy level. It's on the same plane as the 4th energy level, but remember, D's are energy level -1, so it's in the 3rd energy level, okay? All right, so the next thing we're doing is we're talking about electron configuration. And electron configuration is, it shows where all the electrons are in the atom. And you have to follow what's called the off-ball principle. All right, the off-ball principle says that you must fill up the lowest energy level orbitals first. And the order for that is this: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, and then 7s. And we won't go higher than 7s in this class. And you say, well, where does that come from? It's the same as the order on the periodic table. So, yes, you need to know this, but it's not that hard, because if you look, where's 1 and 2 elements? What are they in? 1s, right? Then where's the 3rd and the 4th element? What are they in? 2s. So we go 1s, then 2s. Then where's element 5 through 10? 2p, right? So you see how it's just going in order? It's 1s on the periodic table, then 2s, then 2p, then what's after element 10? You have 11 and 12. What's that in? 3s. Do you guys see that? Then what's after 3s? Element 13 through 18 is in 3p. Then after 18 comes 19 and 20, which is in 4s. Then 21 through 30 is in 3d. We're just going in order. Then 31 through 36 is in 4p. Do you guys see that? It's just going in order. Then after that's 5s, then 4d, and so forth. And there you go. So when we're doing electron configurations, you have to show where all these electrons are. So this is the order here, and you have to start with the lowest energy level first. So I want you to think of this. Think of electrons as ping pong balls, right? And that these are buckets. And the S All the S sublevels have one bucket. You could fit 2 electrons, 2 balls per bucket. And then the P's are going to have 3 buckets because you can fit 6 total, right? And then the D's have 5 buckets because you have 5 orbitals. And the F's would have 7 buckets. So if I'm doing the electron configuration, we're going to say for phosphorus, all right? Well, phosphorus, here's how you do it. Phosphorus is P, and it has 15 electrons. Because remember, the electrons are the same as the protons. So if you know the atomic number, you know the number of electrons. So phosphorus has 15. I have to account for 15 electrons. What is the ending electron configuration for phosphorus? It's going to be 3p what? 3, right? Because it's the third one. 1, 2, 3, NP block. It's right here. So it's 3p, 1, 2, 3. All right? So that's what I'm going to end in, right there. You say, okay, so here's my list, and I'm going to finish with 3p. I'm going to finish in 3p. If I finish in 3p, that means everything up to 3p is filled. So what's going to be filled? It's going to be 1s2, then 2s2, then 2p6, then 3s2, then 3p, and I'm only using 3, not 6, 3, because that's my last electron configuration. That's my ending electron configuration. So, the way you can check yourself is you can add them up. So add up the superscripts. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15. That's how you know you got it right. Because when you add up the superscripts, you're adding up the electrons, you've accounted for all 15 electrons. Okay? You see that? So you have to fill up each sublevel and the orbitals in each sublevel, and you have to go from the lowest to the highest. Now, the long version of that would be 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, and 3p3. Now this would be individually saying each electron where it's at. But that would drive you bananas, right? If you had to write that much out for each one. So rather than doing 1s1, 1s2, you can just write 1s2, and this accounts for both of those. And then 2s2, this accounts for both of those. And then 2p6 accounts for all 6 of those. 3s2 accounts for both of those. And then 3p3 accounts for those 3. You see that? So this is the electron configuration for phosphorus. All right. So what if I did a harder one? What if I did, let's do silver, Ag. All right, Ag is 47. So I have to account for 47 electrons. What is its ending electron configuration? 4 what? 4d, and it's 9, 49. So my ending electron configuration is 49. So this, to me, makes it easy. I know how many I have to account for, and I know where I'm finishing. Okay? That way you can't get confused. So then I say, okay, I'm finishing in this sublevel here. Okay? And so that means everything up to that is filled up. Okay? So what's the first thing? It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d9. You say, well, how did you know that? The more you do it, you just get it. You know it because you just go through it every time. It's the same order every time. So the more you practice, the better you get. Okay? So how can I check it? 2 plus 2 is 4, plus 6 is 10, 12, 18, 20, 30, 36, 38, 38 plus 9, 47. Okay? It's 47 electrons accounted for. Everybody see that? Any question of that? Okay, now, so that's electron configuration. The next thing is the noble gas notation. This is going to be your best friend. So rather than writing the whole thing out, the noble gas method, or noble gas notation or shorthand method, sometimes it's called a shorthand method, it says you put the noble gas that comes before the element, and then you fill in the rest. So what is the noble gas that comes before silver? Krypton, right? See where silver's at? 47. What's the one that comes before 47? 36, right? So by me putting krypton in a bracket, that represents 36 electrons. You don't have to write the 36. I'm just showing you that that represents the first 36 electrons. Okay? So that represents on this thing here all the way up to here. So by putting krypton in that bracket, that means all of that is represented with that. Then you have to finish it. So after 4p6 comes 5s2 and 4d9. And then you're done. So you just have to show the outer part after the noble gas. That's what comes after the noble gas is what you have to show. Do you see that? So let's do it for manganese. So manganese, Mn, what's the noble gas that comes before manganese? Argon, right? So I put argon in parentheses. That represents those 18. And then I got 4s2 and 3d5 after that, because manganese is 25. So this represents 18, and then I have 7 more, 4s2 and 3d5. Do you see that? So that's called the shorthand method or the noble gas notation. All right? We'll do one more. What if I gave you barium? Barium has 56 electrons. But look how easy this is. What's the noble gas that comes before barium? Xenon. And then all you have left is 6s2. Because xenon represents 54 electrons. Right? How do I know that xenon's 54? Because that's its atomic number. Right? So that represents 54. All right. So any questions with noble gas notation or electron configuration? Are we good? Okay, the next thing is called orbital diagrams. Okay, orbital diagrams are going to show the electrons in their orbitals and their spins. So now you actually have to physically represent the electrons by arrows. Okay, and so you're going to see that when you represent them, you're going to have up arrows and down arrows, and you're going to have the electron configuration still going to be there. So you're going to have 1 and then S. You don't have to write 2. You can if you want. Some teachers get really mad about that because like that's extra information. Just write 1S and then put the 2 arrows. That represents the 2. But me, I just like the accounting of it of 1S2 and then I know I have 2 arrows. 2S2, I know I have 2 arrows. 2P4, I know I'm putting 4 arrows in there. But you can just write 2P and put 4 arrows if you want. You don't have to write the 4. All right, now, there's 2 rules you have to follow when you're doing actually 3 rules. You have to follow Pauli's or off-Paul's principle, and then you have to follow Hund's rule and Pauli's exclusion principle. Well, Hund's rule is called the school bus rule, all right? And a school bus rule means what? It means you have to fill up each empty orbital with 1 electron before you double up. Just like if you were getting on a school bus. Okay, we'll say we're getting on a school bus, all right, and this, you're taking the little bus, we'll say, all right, is what it is. All right, so what's going to happen when you get on the bus, Bella? You're the first one on the bus, you don't know anybody, it's the first day of school, where are you going to sit? You get 3 options.
Probably in the middle.
Middle, all right, so Bella's going here. All right, so where are you going to sit? Where are you going to sit? At the end? All right? Boom, all right? And then you're coming in, where are you going to sit?
At the front.
In the front. Now, it would be creepy if there's an open seat, you don't know anybody, and you just sidle up next to somebody, right? Like, wait a minute, what? Dude, there's an open seat right there. Well, that's what this rule is stating. Okay, it's the same thing, so you did it right. So you pick up, you have to fill up each empty seat before you double up. Okay? So that's what this is. So if I'm filling this up, and we're saying what's 2p4 is oxygen. So this is the orbital diagram for oxygen, which is going to end in 2p4, and I have to account for 8 electrons. So the first 2 are in 1s. I draw the box that represents the orbital, and s's only have 1 orbital, so they'll only have 1 box. And then I draw 2s, and I've got 2 electrons, up, down. Okay, and then I've got 2p, and I've got 4 electrons. So it would be wrong to do up, down, up, down. Why is that wrong? Because I didn't fill up each empty seat, right? So what you have to do with this is you have to fill up 1, 1, 1, then you double up. Okay? So a 2p4 is going to be up, 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 and then 1 down. So you got to fill up all the empty orbitals before you double up. All right? Now, Pauli's exclusion principle is our next thing you got to follow. And that means that you can have a max of 2 electrons per orbital, which we saw that, and they must have opposite spins. So that's why you have to have an up arrow and a down arrow. Okay? It would be wrong if you put 1s and both arrows going up. Okay? That would be wrong. It has to be up and down. Okay? You got it? It has to do with the like the electricity and all that stuff. Like they have to have opposite spins. Now, so what is the shorthand for this stuff? Well, we'll say I'm doing cobalt. Okay? Cobalt has 29 electrons. So rather than drawing the box, now you guys listening because you got to follow directions on this. Rather than drawing the whole box, you can just put a line. That represents the box. And rather than drawing a whole arrow like this, you can draw half arrows like that. So that represents the same thing as that. So rather than drawing the box with 2 big arrows, you can draw a line that represents the orbital with a half arrow. But when you get to the P's, okay, you have to draw 3 separate lines. It cannot be 1 line across. If you draw it like this and then just put up, 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 down, 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 that's going to be marked wrong because you have to have 3 distinct orbitals. Okay? So if you don't want to do that, you want to do it like this, where you just draw 3 boxes, then do that. Or if you want to draw 3 lines like this, it'd be up, 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 then down, down, down. Okay? It just saves room because some of these, if you have to draw 52 arrows, that's a lot of arrows. All right? Now, so that's how you do the shorthand version for this. Now, cobalt, we got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it finishes with 3d7. So how many orbitals did the D block have? 5. So you have to draw 5 lines because there's 10 possible electrons, 5 orbitals, right? So I draw 5 lines, 1, 2, 3, 4, 5. I put 1 in each because that's Hund's rule. Then I double up, and when I double up, it's got to be opposite. So that's 7 arrows. Okay, you see that? All right. So there is no shorthand. There's no shorthand orbital diagrams. So if you do an orbital diagram, you got to do all of it. Okay. All right. So any questions with orbital diagrams versus electron configuration? Yeah.
Wait, so would there be empty spaces if you don't have less than 5?
Yeah, great question. So what if it was a 3D2? You still have to draw 5 boxes or 5 blanks, but you only have 2 electrons. So there'd be 3 empty boxes. That's a great question. All right. Any other questions? All right, you guys can stop it. Thanks.